Welcome to this first video of my playlist about the most practical ways to prepare benzonitriles. This video is about the conversion of aryl halides or sulfonates into benzonitriles. In the second video of this playlist, we'll have a look at the conversion of anilines into benzonitriles by intermediate formation of diazonium salts. Ammoxidation of methylarenes, benzylic alcohols, amines and chlorides will be discussed in part 3, and part 4 is about the electrophilic cyanation of unsubstituted arenes. Finally, in the last video, I'll show you some strategies for the conversion of carboxylic acid derivatives into nitriles, for instance trihalomethylarenes, benzoic acids, amides or esters. In my channel you can also find a video playlist about the preparation of aliphatic nitriles by alkylation of cyanide. Nitriles are versatile intermediates and can be converted into many other compound classes, for instance amides, carboxylic acids, orthoesters, amines, aldehydes or ketones. Aromatic nitriles are not manufactured on such a large scale as for instance acrylonitrile. Still, benzonitrile, chlorobenzonitriles and some cyanophenols are important intermediates for dyes, agrochemicals, pharmaceuticals and polymers, and hundreds of tons are produced annually. The technically most attractive synthesis is ammoxidation of alkyl benzenes, as shown here. These are usually continuous gas phase reactions that require dedicated plants. As an alternative, trichloromethylarenes can be converted into nitriles by treatment with ammonia or ammonium chloride. We'll have a look at this reaction in the last video of this playlist. It is also possible to prepare nitriles directly from benzoic acids and ammonia by intense heating, but structurally more complex benzoic acids may undergo other thermal transformations and not be suitable starting materials. All three chlorotoluenes can be converted into chlorobenzonitriles by ammoxidation. The cyano group is electron withdrawing and can promote aromatic nucleophilic substitutions. 4-chlorobenzonitrile, for instance, reacts with sodium methoxide under forcing conditions to 4-methoxybenzonitrile and then to the sodium salt of 4-hydroxybenzonitrile by nucleophilic demethylation. Nucleophilic additions to cyano groups are often slow and did not significantly compete with the aromatic nucleophilic substitution of chloride in this case. With sodium hydroxide, however, saponification of the cyano group occurred. There are three main strategies to convert aryl halides into nitriles. The most economical is direct, uncatalyzed aromatic nucleophilic substitution with sodium, potassium or tetraalkylammonium cyanide. This only works well with electron-deficient arenes and often requires phase transfer catalysis, dipolar aprotic solvents, high reaction temperatures and a high concentration of reactants. A second strategy is the use of stoichiometric amounts of copper cyanide. Examples have also been reported of the use of catalytic amounts of copper cyanide, but usually more than one equivalent is required. Main disadvantages of this strategy are the increased costs and the large amounts of copper waste. Moreover, with most starting halides, a high reaction temperature will still be required. Milder reaction conditions can be attained with the aid of palladium or nickel complexes as catalysts. Unfortunately, palladium and the required ligands are expensive, and because of the large number of additives and other parameters, such reactions can be difficult to optimize. Purification of non-volatile nitriles can also become an issue. Uncatalyzed cyanations are normal aromatic nucleophilic substitutions, with the only peculiarity that cyanide itself increases the reactivity of the arene. Fluoride is the best leaving group among the halides, and iodide the worst. The precise leaving group order will, however, depend on the structure of the starting arene. In the case of substituted pyridines, sulfonyl groups are displaced more readily than bromide or chloride, while the reverse is true for substituted benzenes. Aromatic nucleophilic substitutions proceed by addition of the nucleophile to the arene and formation of an intermediate carbanion. Thus, electron-withdrawing substituents capable of stabilizing this carbanion will decrease its energy and enhance the reaction rate. Aryl halides with such groups at the ortho or para positions, and 2 or 4 halopyridines undergo nucleophilic cyanations more readily than other isomers. Let's check some specific examples of transition metal-free nucleophilic cyanations. Chlorobenzene is not particularly reactive toward nucleophiles, but can be converted into benzonitrile with unsolvated cyanide. Like fluoride or hydride, cyanide is a small anion and the electric field strength on its van der Waals surface therefore very large. This causes the formation of strong bonds to solvents, in particular to protic solvents, which then decrease the nucleophilicity of cyanide. Unsolvated cyanide in an unpolar aprotic solvent such as chlorobenzene, however, is a powerful nucleophile. The more so, the larger the distance to the cation. In this example, a bulky phosphonium salt was used to dissolve cyanide in chlorobenzene, and at 130 degrees Celsius the substitution was complete after 2 hours. A similar reaction with pentachloronitrobenzene in ethanol, however, did not proceed at all, not even at 200 degrees Celsius. Solvation by the protic solvent completely shielded the cyanide anions and kept them from adding to the electron-deficient nitroarene. As expected, fluoride is displaced more readily in aromatic nucleophilic substitutions than other halides. In this example, fluoride could be selectively substituted by cyanide by treatment with a slight excess of zinc cyanide in DMSO. Nitroarenes are usually more reactive than benzotrifluorides, and in this example, a selective monosubstitution could be achieved in dimethylacetamide at only 40 degrees Celsius. Orthofluoride was displaced more readily than fluoride para to the nitro group. Also, halogenated benzoates can be suitable starting materials for aromatic nucleophilic substitutions, as shown here. A complete displacement of fluoride occurred in only 3 hours at 60 degrees Celsius, without any nucleophilic demethylation of the ester. At 150 degrees Celsius, and with a larger excess of potassium cyanide, however, also the ester was saponified. Electron-donating substituents can decrease the rate of aromatic nucleophilic substitutions, but the strength of this effect is difficult to estimate correctly. In this example, a halogenated nitroaniline underwent a clean and selective substitution by treatment with sodium cyanide at room temperature. Also, unprotected phenols may undergo clean substitution reactions, as in this example. Again, the halide para to the electron-withdrawing acetyl group was displaced selectively. Occasionally, the activating groups themselves may also be displaced. Particularly good leaving groups are sulfonyl and nitro groups. Here, both fluoride and a methane sulfonyl group were substituted by sodium cyanide in refluxing DMF. In this example, fluoride could again be selectively displaced from a trihalopyridine, although both the 2 and 6 positions of pyridine are reactive, and despite the additional activation of the product. Such reactions may require careful optimization. Also in this example, the starting pyridine contained 2 displaceable leaving groups. By choosing the right conditions, either only one or both groups could be substituted. Because aryl sulfones readily undergo aromatic nucleophilic substitution, sulfinates can sometimes be used as catalysts for such reactions. Here, for example, chloride was displaced by cyanide with the aid of an excess of sodium toluene sulfinate. Unfortunately, sulfinate may also act as an oxidant and cause oxidative cyanations. With a similar starting pyridone, the same conditions yielded mainly a product of twofold cyanation, probably through oxidation by the sulfinate, as shown here. Transition metal-mediated cyanations are more complex than simple aromatic nucleophilic substitutions, and the precise mechanism can depend on the ligands, solvent, and other additives. The mechanism of aromatic cyanations with stoichiometric copper cyanide has been investigated carefully, and no radicals seem to be involved. The electronic properties of substituents in positions 3 and 4 have little effect on the rate, and the leaving group order does not correspond to that of uncatalyzed aromatic substitutions. One plausible mechanism would be a concerted cleavage of the carbon-halogen bond and formation of the new carbon-carbon bond, as sketched here. Polar aprotic solvents like pyridine or DMA combined with high reaction temperatures are usually required to attain reasonable reaction rates. Here the relative rate of nucleophilic cyanation with an excess of copper cyanide in dimethylacetamide is shown for a selection of substituted aryl halides. Iodides react fastest, and orthocarboxylate strongly enhances the reaction rate, perhaps through coordination with copper. This is a typical cyanation with stoichiometric copper cyanide. Although both halides were activated by the methoxycarbonyl group, the orthochloride was displaced selectively and in good yield. As mentioned above, however, no activation by electron-withdrawing groups is required for transition metal-mediated nucleophilic cyanations. Here, for instance, a 4-bromoaniline was cleanly converted into a benzonitrile, without any activation of bromide by electron-withdrawing substituents. Again, a high reaction temperature was required. In this example, only half an equivalent of copper cyanide was used, together with a slight excess of sodium cyanide. The chloride activated by the nitro group was displaced preferentially. Aliphatic nucleophilic substitutions with copper cyanide are slow, and selective aromatic cyanations can be achieved even in the presence of aliphatic halides. In this example, the cyanation of an aryl iodide proceeded faster than cyanation of an aliphatic chloride. The ease with which halides are substituted by copper cyanide correlates inversely with the carbon-halogen bond strength. Here, bromide was displaced faster than fluoride or chloride in a halogenated pyridine. Similarly, also here the carbon-iodine bond was cleaved preferentially. Despite the large excess of copper cyanide, no displacement of chloride occurred. The mechanism of nickel or palladium-catalyzed cyanations consists of an oxidative insertion of the metal into the carbon-halogen bond, followed by ligand exchange and reductive elimination. Bulky bidentate phosphine ligands prevent the precipitation of the metals and the formation of stable, unreactive metal cyanides. Reducing agents, such as metallic zinc, are often added to regenerate the reduced nickel or palladium. A low cyanide concentration is often helpful to prevent the formation of unreactive metal cyanides. This can be attained by slow addition of cyanide or by using some cyanide of low solubility or hexacyanoferrate as cyanide source. Other potential ligands, such as 1,2-diamines, diols or amino acids, may also form stable, unreactive complexes with the catalyst and thereby inhibit the cyanation. In transition metal-catalyzed nucleophilic cyanations, electron-withdrawing substituents at the arene sometimes slow substitution down, while electron-donating substituents can increase the rate. Sterical accessibility can also have an impact on the regioselectivity of these cyanations. This is a typical example of catalyzed cyanation of an aryl chloride. The substitution proceeded in acetonitrile at 80 degrees Celsius, and because of the bulkiness of the catalyst, only the sterically most accessible chloride was displaced. Even sulfonates can sometimes be substituted, despite the strength of the carbon-oxygen bond. Zinc cyanide was the cyanide source in this instance. Aryloxytriacenes also seem to be suitable starting materials, and more reactive than aryl bromides. These triacenes can be prepared from phenols and cyanuric chloride. Despite the excess of cyanide, no substitution of bromide occurred. In this palladium-catalyzed cyanation, a substituted benzaldehyde was converted into a cyanobenzaldehyde with potassium hexacyanoferrate as cyanide source. No cyanohydrine or benzoene was formed, and the expected substitution product was obtained in high yield. This is an example of a selective monocyanation of a dibromide. Only the bromide para to the electron-donating amino group was displaced. Under these conditions, no cyanation of a similar dibromo-dinitrobenzene occurred, because the chosen catalyst preferentially inserted into electron-rich carbon-halogen bonds. Similarly, dibromocatechol was unreactive under these conditions, probably due to poisoning of the catalyst by chelate formation. As with copper cyanide, palladium-catalyzed cyanations preferentially displace aromatic halides and not aliphatic ones. In this example, an aryl bromide reacted faster with cyanide than an alkyl chloride. The latter remained unchanged, despite the excess of zinc cyanide and the high reaction temperature. This is another example of aromatic nucleophilic cyanation of an aldehyde. The yield wasn't high, but it is amazing that the product could be isolated at all. Aldehydes tend to undergo benzoene condensation in the presence of catalytic cyanide. In order to cleave the strong carbon-chlorine bond, a bulky phosphine-terz-butylphosphine complex was used as catalyst. Another suitable source of cyanide can be acetone cyanohydrine. To prevent poisoning of the catalyst, the cyanohydrine was added slowly to the reaction mixture while the substitution proceeded. Besides an excess of a tertiary amine and isopropanol as solvent, no additional reducing agent was required in this instance. Other functional groups that can be displaced from arenes by cyanide include thioethers and amino or chlorocarbonyl groups. There are, however, simpler strategies to convert the latter into nitriles, which I discuss in part 5 of this video playlist. Let's have a look at the most common side reactions. In the presence of reducing agents, palladium and nickel complexes readily bring about the formation of biaryls from aryl halides. Sometimes it's almost impossible to prevent the formation of these products, and if this is not acceptable, for instance if the biaryls are a toxicological or environmental concern, another synthetic strategy must be chosen. Cyanide can also act as reducing agent, and sometimes products of reductive dehalogenation may result as byproducts. Here, around 6% of such a dechlorinated nitroarene was formed, together with a small amount of benzamide, another type of potential byproduct. Sometimes nitro groups are displaced more readily than halides, as in this example. This seems to occur more frequently with polychlorinated nitrobenzenes and with phase transfer catalysis in apolar solvents. Because of the high basicity of cyanide, I would not have chosen chloroform as a solvent, but this did not seem to cause any problems here. Also, sulfonyl groups may be displaced by cyanide, and the resulting sulfinate can compete with cyanide for the remaining electrophile. In this example, large amounts of disulfone were formed by displacement of chloride from the starting material by potassium methane sulfinate. Interestingly, almost none of the expected cyanosulfone was obtained. Nitroarenes may also undergo oxidative cyanation by adding cyanide at an unsubstituted ortho or para position. Such additions can yield a large number of unexpected products. Here, for instance, a low yield of 2 isomeric methoxybenzonitriles resulted upon treatment of dinitroaniline with an excess of potassium cyanide in methanol. The mechanism was probably similar to that of the Neff reaction, in which a nucleophile adds to a deprotonated nitroalkane. Here, methanol added to the first intermediate, and elimination of the nitroso group then yielded the final products. If this reaction is conducted in the presence of an oxidant, such as potassium hexacyanoferrate, the reduction and displacement of nitro groups can be suppressed, and products of oxidative cyanation can be obtained in reasonable yields. Also, benzoic acids may result when nitrobenzenes are treated with ionic cyanides, in the so-called Richter rearrangement. Yields are only low, but the mechanism of the reaction is interesting. It involves a large number of intermediates, what is probably the reason for the low yield. One only rarely seen transformation during this complex reaction sequence is the formation of a nitrogen-nitrogen bond by intramolecular condensation of a nitroso group with an amide. The resulting acylated azo compounds are strong electrophiles that readily acylate nucleophiles. Here, saponification and radical or ionic fragmentation and release of nitrogen yielded the final benzoic acid. On this and the next slide there are some more, mostly recent examples. You can also find these references in the description of this video. The next video of this playlist is about the conversion of anilines into benzonitriles by intermediate diazonium salts. Because of the ready availability of anilines and the low cost of the required reagents, this approach is attractive. Unfortunately, the reaction is not easy to perform, but a good understanding of its mechanism and potential problems should increase the odds of success. See you then.